Welcome to the future. Technologies and innovations that sculpt our industry. This session was recorded live at the 2023 National HVACR Education Conference. To learn more about Midea, visit midea.com. All right, Kyle Hunter from Midea, thank you so much for joining us today. So let's talk a little bit about inverter technology, right? Inverter is one of my passions. We've spent a lot of time talking about, incentives that will be coming way for contractors and homeowners, hopefully through things like IRA, in really investing in the electrification of America. So in that, as technicians, we have a lot to learn. We have a lot to understand, and in our educational programs, many of us end up in training that really haven't dove into inverter technology a lot. And we've had a great conversation about inverters. So let's talk a little bit about operational conditions inside of an inverter. What's happening outside? We have a lot of thoughts, but let's talk about what's actually happening in our outdoor unit.
So the inverter is not a magic box. It's not something that you just have to accept what's going on and just go, oh, it's doing its job because the compressor's running. Well, what job is it doing?
Yeah.
And really, the inverter is just, it's an old term that a lot of people understand as a freak drive, a frequency drive.
Variable frequency.
And that's exactly what we're doing with an inverter, is changing the frequency. Because if you understand motor drives and how many poles or winding sets a motor has, that sets your speed of your motor. So if you have a 2-pole bathroom fan hooked to 60 hertz, it's going to run at a potentially set speed of 3,600. You have drag, you have load that will never reach 3,600, but that's the potential. That's the max potential. And so what the inverter does is it takes that 60 hertz and it will just take it and modulate the speed. And on all the inverters, you have a 3-phase motor hooked to a single-phase source. For the most part, residential single-phase.
Yeah, in residential applications.
And so you have that single-phase source. You have only 60 hertz. You can take that, 230 volts, and you rectify it with diodes, and that's the first phase of an inverter, is a rectifier. It takes the 230, rectifies it optimally to 310 volts DC.
Exactly.
310 volts DC through some capacitors and what's called a reactor to kind of clip and make the voltage as clean as and flat as possible.
Right.
And then you have these gates, switches.
Switches, basically.
IGBTs, insulated gate bipolar transformers, transistors. Sorry, and all they're doing is turning off and on at a set speed. Yeah. And that set speed, when you have your DC positive and your DC negative, you turn on the positive gate, you turn on a negative gate, you have a circuit.
Yeah.
And then you flip them, and the same gates. You flip them, and now you have your positive below and your negative on top, and you create a sine wave. So you just alternate up and down on those insulated gate transformers, and you can create a sine wave.
Exactly.
Now,
so it's a simulated sine wave.
It's a simulated sine wave. You don't just turn on and off. These transformers, they're time-based transistors.
That's right.
They're time-based, so the longer they stay on, the more voltage is allowed to pass. And you can also turn them on a little bit. You apply smaller voltage, you get some leak through. You apply full voltage, you get the full 310 volts.
Okay.
So you can stagger them on. So you go slight voltage, a little bit higher. You get that nice slow opening.
Nice light.
And then you have your nice slow closing, and you alternate that, and then you have your nice smooth sine wave instead of a square sine wave. Because that's, when we first had them, that's what we had. We had slower processors, and so we can only do on and off. And the speed of our transistors, our processors, dictated that.
Okay.
Now we have faster and better electronic components,
Yes.
and we can go a lot quicker stages.
Okay.
So we have that nice smooth sine wave. And you get 6 of these sets,
Right.
you get your 3-phase. And so on a motor, on a compressor, you have U, V, and W.
Yep. Our 3 phases
You have a U positive and you have a U negative IGBT
of our
on the board.
gates. Okay.
You have a V positive, V negative, W positive, W negative.
Okay.
And so it just alternates those, gets your speed, gets your voltage, also is modulated. So that way, when you're running at a slower speed, you have the right amount of voltage to still have the proper torque.
Yeah,
your
the
motor.
torque load. Right.
And so it just doing that. It's not sci-fi.
Yeah, exactly.
It's
It's just something new.
it's something new.
Yeah, absolutely.
And testing a compressor is no different than testing a 3-phase house system blower.
Yeah, exactly.
If you have a big 3-phase motor, 3-phase pump, 3-phase anything that
Same
you've
resistance between windings.
20, 30 years ago,
Yeah.
you just ohm out your windings. On most compressors, they're very low
It
resistance,
is.
hardly ever over 2 ohms.
Yeah.
And the key is, I don't care what the resistance is. I don't have it spec'd out on any of my products. As long as they're the same.
Things are the same. We're running identically.
Yeah. So you disconnect off the terminals, you ohm them out. U, V, W, three readings, under 2 ohms and matching. Compressor's good.
Absolutely. So let's just talk about, let's say, a ductless mini split for a minute, right? So
I love those.
Oh, I bet you do. I know it's why we're having this conversation. You're a very intriguing person, and I love talking to you about this because you have a very good way of simplifying the operation of a ductless mini split. So let's think about the primary components of our outdoor unit, and let's mentally visualize how each of these components are operating, how they're responding.
So you have your compressor, you have your outdoor fan motor, and your other load that a lot of people don't think about is your expansion valve.
Yeah.
On a mini split, those expansion valves, your metering device is on the outdoor unit. So everything's outside.
Yep.
And those 3 units, those 3 components are really isolated components doing their own thing.
Absolutely.
You have your compressor. Your compressor's responsibility is, of course, pump refrigerant throughout the
Vapor
system.
pump.
And its happy point is a cool shell.
Right.
It wants to stay cool. So the hotter the load inside, the hotter refrigerant coming back to the compressor. So it's going to run faster to get cool refrigerant back to itself to stay cool. That's all that compressor speed is doing.
I know it's kind of crazy. When you
I'm
think about
simplifying
that.
it.
Yeah, no.
True.
This is what we want.
It is a very, it might be oversimplification, but that is in the logic.
Yeah.
The compressor speed is really dictated by how hot the compressor is.
Yeah. Okay.
It doesn't care about the indoor temperature. It knows the indoor temperature because of how hot the refrigerant coming back is.
Yeah. It's not the thermostat telling it how fast to run.
Exactly.
Big misconception in the industry.
It's your discharge sensor on your compressor. It wants to stay cool. It stays cool by speeding up.
Right.
And then
Pumping more refrigerant through the pump.
And then your outdoor fan motor is variable speed as well, and it's going to try to keep a certain temperature.
On the
so
coil.
that way your saturation levels are proper
Maintains.
coming out.
Exactly.
And so that's going to speed up and slow down depending on
Based on the temperature of the coil.
exactly.
Yeah.
So low charge is going to cause the fan to go slow.
Sure.
It's not going to go faster. It wants to build up the heat. And if there's not enough refrigerant in the system, the fan's going to slow down to build up the heat.
Okay. So the fan can be running at a disproportional speed of the compressor. And it's because they're running fairly isolated from each other.
Yeah. So, and then you have your expansion valve.
Yep.
Your expansion valve is really also looking at the temperature of the return and the temperature of the supply of your refrigerant.
Yeah.
And so it's going to modulate. It's going to open and close.
Do what a metering device likes to do.
It's going to try to keep that calculated superheat.
Yeah, we can superheat. It does exactly what every metering device has ever done.
And the odd thing is, it's in the outdoors. So
Yeah.
technically, from your service port, back to the service port. That is your evaporator, and that's why
the
it's
entire
critical.
system.
That's why you insulate the line
both
set.
lines. Yeah.
Yeah, you want to minimize your heat
Heat
loss,
loss.
from your outdoor unit back. And so the expansion valve is going to open and close to keep that temperature.
Right.
So you have those three components working in concert with each other, trying to maintain a harmonic, cooperative system.
Yeah.
And so if you run into a charge issue, your compressor is going to go faster because it's going to get hot.
Yeah.
And your amp draw might drop because the load goes away. Your expansion valve is going to open up too far because the temperature difference is not going to be there. So your expansion valve is start going to open almost full.
Yeah.
Your fan, outdoor fan, is going to slow down because there's no refrigerant to build heat
No
on
temperature
the
on the
coil.
cans there. Yeah.
And so one thing that's really nice with some diagnostic tools, you can see those three components.
Right.
When you understand the system, you can see what is my amp draw, what's my compressor speed, what's my discharge temperature, is it too hot, what's my expansion valve. That is a good sign
All indicators
of a
performance.
of a issue.
Yeah.
If I have a 700 step EEV and I'm running over 600 steps, there's something wrong with the system. It should never get that high.
Yeah, exactly.
But
Very
yeah,
cool.
when you learn what those three components are trying to do individually to work together to create a cool indoor, you can understand how to see the operating system.
I love it. Love it. Simplified to a point where we take out some of the demystification, talk about the future of our industry, because we are definitely moving towards inverter technology, and many people are afraid because they don't understand the operation. When we talk about inverters, many people have told me that there's no sequence of operation on an inverter or a mini split. I'm like, are you kidding me? Everything has a sequence of operation.
Everything does, yeah.
You know, we don't have inputs without, or don't have outputs without inputs. So what they are doing, they are working very independent to form a complete operating system. So when we're looking at particularly in this scenario, our ductless inverter, we're looking at three different scenarios, all operating simultaneously. So we have sequences to look at for each one. So take the time, learn a little bit about the changes in our industry, and welcome to the future of inverters.
It's great. It's wonderful, and it's here to stay. It's something that we have to embrace and
Yes, we do.
understand and work with. And when you know the systems, you're going to be able to increase that profit because you're going to minimize your returns. You're going to minimize your guessing.
Yeah, exactly.
That's the biggest problem is the guessing.
Yeah.
How many boards have been replaced? It's disproportionate.
Oh, absolutely.
There's so many boards being replaced for no reason other than the technician doesn't understand what the system's doing, and so it has to be the board.
You know, we run into this topic quite often in the commercial applications, in the commercial HVAC industry. The replacement parts ratio is somewhere around 6 to 7%. When we get into the residential side, now we're getting up over 60%. What's the difference between the residential and the commercial?
The skill
Education.
level of technician.
That's it.
Yeah.
And that's what we're here for, is to help simplify these things that are changing in our industry and just bring you closer to the future of technology. Thanks, Kyle.
Hey, it was fun.
It was a blast.
Thank you.